We're going to review something called complex arithmetic. Complex arithmetic is arithmetic that involves the square root of -1. We use the lowercase I to represent the square root of -1. When we add I to itself, we just do this like we would any other variable. I plus I equals 2I. I plus 2I equals 3I, so on. I times I is I squared, and I squared equals -1. That's the main thing that makes complex arithmetic more complicated. I cubed would be I times I squared, which turns out to be -I. And then I to the fourth, it's -I times I, and I squared is -1, so it's -1 times -1, which is 1. So this pattern repeats itself. I to the fifth is I to the sixth power is -1, I to the seventh power is -I, and I to the eighth power is 1. So every additional I causes this to move through here. Every 4 additional I's causes this to move through this cycle. We need to be able to add complex numbers. So let's let W and Z be complex numbers. If we add W and Z, made a little mistake here. If we add W and Z, we add their real parts together, and we add their imaginary parts together. So these are the real parts, and these are the real parts here. And these are the real parts here. Here are the imaginary components. And we add those together, and we leave them with the letter I. Okay, multiplying. Here we're multiplying two imaginary numbers, W and Z. For their product, we have to use the distributive property of multiplication over addition. You can easily work this out for yourself by using FOIL. The terms are the real parts, the imaginary parts, and then we end up with a negative real part. But you can actually combine this so that it's AC minus BD plus I times AD plus BC. In complex arithmetic, there's something called the complex conjugate. The complex conjugate of a complex number is found by keeping the real part, here A, and by changing the sign of the imaginary component, which is B times I. If you multiply a number times its complex conjugate, you get the sum of the A and B components squared. And if you apply the FOIL method, you can prove that to yourself readily. Dividing complex numbers requires us to use the complex conjugate. If we have the quotient of two complex numbers, W divided by Z, we can evaluate that by multiplying both the numerator and the denominator by the complex conjugate of Z. That will make the denominator real. Then you'll be able to divide both the real and imaginary components of the product w times the complex conjugate of z by that real number. So all that you have to do is remember to multiply the numerator and the denominator by the complex conjugate of the denominator.